Welcome. Hello, everyone, and welcome to NSTA web seminars, where you can find live, interactive learning at your desktop. Today's seminar is How Do I Promote Student Modeling? Our presenters are Cynthia Passmore and Jennifer Horton. My name is Dorothy Jeanette, and I will be moderating tonight's program. Let's get started with an introduction.
Yes, hello everyone. Ted Willard here, Director of NGSS at NSTA, and I just want to give you a little bit of a background on the series that we're doing right now. A few weeks ago, I had the privilege to work with Tricia Shelton to do a session on how do I select phenomena to motivate student sense-making. Tonight, we are looking at how do I promote student modeling with Cindy Passmore and Jennifer Horton, and then we'll have on May 10th, a session on how do I promote student discourse with Kate McNeil and Eric Muniz. And July 12th, how do I develop a storyline for a unit with Brian Reiser and Michael Novak. Each of these sessions couples a science education researcher with a classroom teacher to really give you all a sense of how you can really start to engage in three-dimensional teaching and learning. And so I'll pass things now back on to Dorothy to formally introduce our presenters.
Hello, everyone. I'd like to introduce today's presenters, Cynthia Passmore, PhD from the University of California, Davis, and Jennifer Horton from Western Placer Unified School District. And I encourage both of you to give us a brief introduction.
Hi, this is Jennifer Horton, and I've been teaching biology for about 11 years. And the past 6 years, I've been heavily introducing model-based reasoning into my classroom, and it has dramatically changed the way I interact with my students and the way that my students learn science.
It looks like we may have that Cindy Passmore's connection has dropped out for a second. While she gets in place here, perhaps Jennifer, you can tell us, give us a little bit of a preview of what we're going to discuss tonight, because I think she's going.
Right, sure, no problem. So Cindy Passmore is a PhD at University of California in Davis, and she has been working with pre-service teachers and model-based reasoning for several years. I was fortunate enough to work with Cynthia during my my credentialing time. And tonight we're going to be looking at how do you promote student modeling in the classroom? What does it look like, and how can we get started so that our students can really start making sense of science instead of just being fed a bunch of science information?
Cindy also happens to be one of the editors of a recently published book from NSTA Press, helping students make sense of the world, the next generation of science and engineering practices. I think I would encourage you to all look at it at some point, as it has chapters that outline each of the 8 science and engineering practices from the next generation science standards and the framework for K-12 science education. I know my own experience with Cindy doing a web seminar for us way back in 2012 on modeling really provided me some important insights about what we were looking for in scientific modeling. I think she's going to talk about some of that for us this evening, because it gave me a sense of, why was the model of a cell that I remember doing in my classroom, what I remember doing in school, not exactly appropriate. We've got, I think, a little bit of a highlight on that. But Jennifer, I'll let you get things started here.
All right. So we're going to go ahead and get started here. And it looks like we have a poll.
Hello, everyone. This is Dorothy. I'll go ahead and run the poll, Jennifer.
Thank you.
So I've given you the polling button, and this time there are 5 choices, A, B, C, D, E. for what's your role in education. So everyone should have access to polling buttons on their devices, so please find that and enter your choice. If, however, you do not, you can type it in the chat, but we prefer to get it in as clicking on the polling button underneath your participant's name. And we'll give you a minute to complete that simple poll. Yes, and I see some people are doing that. If your role isn't really described here, go ahead and type something in the chat area. Thank you. I'm closing the poll now, and I'll post the information to the slide. Okay, it looks like we have a large number of pre-K-12 classroom teachers, a few informal educators, some professors of higher ed, an administrator or two, and quite a few pre-service teachers too. Welcome everyone. We've got a very diverse and large group. This is fun.
All right, I'm going to fill in here for Cindy until she's able to get logged on. And so the first thing we're talking about is modeling in the classroom, and that there really is a challenge here. This is a big shift from where science teaching has been in the past to where we're going in the future. There's a lot of theory behind this, but the theory and talking about it can look very different than what we actually do in practice, what we actually do in the classroom, teachers and students. And then it's how do we get started? Because this is a big shift. It's not always easy, but it's definitely rewarding once you really get into the modeling and your students are really making sense of the science around them. Cindy picked this quote, which is wonderful, by Rachel Carson, and it's really about that idea that we don't want to tell students. If we tell them things, they don't really remember, and do they really even care? But what we really want is we want students, not just students, we really want everybody to wonder about the world around them and to ask questions and to really make sense of that world and that phenomena that they see. So we're going to look into a middle school classroom and just think for a moment, what do you notice that's going on? And so we can see here that kids are working at a table. They have some clear bins. They have cups of water, some very hot water, and food coloring. And what exactly are they doing? So if we ask the kids what they're up to, which is important for the students to know what they're doing in their own science classroom, one girl says, we're learning about convection currents. See, you put a cup of really hot water under the end of the bin, and here it makes that drop of food coloring swirl around. And another student pipes up, yeah, see, the food coloring goes up at once, and this area is heated. Heat rises, that's convection. And then when you really want to know what they're trying to figure out, is it just about convection, or are they really trying to figure out something else? Are they really testing ideas to try and figure out what's going on with a bigger phenomenon? And here they say, yeah, we're really trying to figure out how a hot air balloon works. See, we have to do these tubs of water and test them. And what do they have to do with hot air balloons? Well, if we put this drop of food coloring at the bottom, then our really hot cup of water underneath, something starts to happen. The food coloring swirling around. And so the girl adds in, yeah, it's kind of like a hot air balloon. If you heat up the water or the air or whatever, and that part goes up, we want to know why that happens. So how do we contrast these lessons? Are they knowing about, or is it really figuring out things? So if we're contrasting these lessons, the knowing about versus the figuring out, the knowing about is that idea that students are being told information, or they are looking, doing a lesson, an investigation, and collecting data, but are they really making sense of that data, and are they really applying it to a bigger phenomenon in the world? And when they're figuring out things about the world, that's where that sense-making comes in, and that's when we start working with scientific models. So here is what we have as the informational frame, and this has been a traditional science classrooms where the teacher is basically feeding the learner knowledge. And here we see more of a sense-making frame. This is a place where the students are really making sense. They're playing. They're trying new things. Some things may not always work, but that's okay. They think about why they didn't work, and they try it again. And they're really making sense of how to put things together. So here we're going to find out on your daily practice on this information frame to sense-making, we want to find out where is your daily practice on this info frame from sense-making, on the sense-making continuum. So if you could use the clip art and on this continuum make a mark of, do you do more information frame in your classroom or sense-making? And thank you. We have all kinds of great responses coming in.
Hello. Remember, you can pick up the clip art. It's to the right of the chat window, and the very bottom icon, which looks like a mountain. And when you go to it, you want to choose, do not use the background. You can choose common symbols and other symbols.
Excellent. It looks like we have people all over the sense-making continuum. That's fantastic. And what this tells me is that we can also learn a lot from each other, which is wonderful. And it looks like we have Cindy back.
I think she's doing a sound check, a sound fix, Jennifer, okay. So just keep going for another minute here. We can get our data, look at the data here.
All right.
Thank you, everyone, for adding in your clip art. And there is a comment by the group from Jennifer.
Hello.
Hello, Cindy.
I'm here. I'm so sorry.
It's okay. We're glad to hear you now.
I'm just trying to see where we are, so I'm clicking back through these slides a little bit. So Jen, you've already done our, can someone catch me up to where we are?
Yes, we were on the sense-making continuum.
So we did all these other slides?
Yes.
Yeah, okay. So it seems like people are kind of in the middle here, but more leaning toward the sense-making frame, so that's exciting. Shall I introduce myself really quickly?
Yes, Cindy, that would be terrific. And I also noticed that there were several comments about how where you are on the continuum of sense-making might be dependent on the grade level you teach. Cindy, I'm going to toggle off so you can introduce yourself.
Okay, great. I'm Cynthia Passmore from the University of California, Davis, and I've been working in this area of modeling and model-based reasoning since I was a graduate student in the 90s at the University of Wisconsin, and an old project called the Muse Project. And I teach here at UC Davis, and I had a class, and I thought I'd set myself up to have this web seminar right next to my classroom, but that was not working, so I had to transport myself across campus. And here I am, and I'm really happy to be here today and talk with you a little bit more about modeling and model-based reasoning in the classroom. So I think we'll just continue. So one of the things that we wanted to talk about today a little bit is where we have come from in terms of crafting and thinking about the practice of modeling with regard to the history and philosophy of science, and some of the ways in which that's framed our interactions with and considerations of the modeling practice as it's described in NGSS. So that's kind of what we're going to transition to here, symbolized by these two heads with years and ideas and whatnot exchanged. So I found this quote a few years ago in a paper by Odenbaugh, which was quoting someone from 1976. Both of these men are philosophers of science, and I thought it was very apt for the way that modeling tends to get talked about and discussed here in the next generation science standards context that we find ourselves in as science educators now. The idea that the word model has many different meanings. It has, in particular in education, we use it in lots of different ways. You might use it to talk about modeling behavior or modeling systems. And all of those have slightly different nuanced meanings that, that matter in the way in which we conceive of and think about this practice. So I think often when we hear the word model in science, these are the kinds of objects and things that we think about. And what I want to push on a little bit today is how we might think about these kinds of objects in our classrooms in productive ways with regard to the scientific practice of modeling. So as my colleagues and I have been thinking about models as they operate in science over time, we've thought about them, and many folks in the history of science and philosophy of science have talked about models as representations of phenomena, as ways in which we distill the important features and relationships within a phenomena in nature that we're trying to explain or account for. And there's nothing sort of wrong with this conception of models. And in fact, it's probably the most common way. But if you think about this, this is positioning models as depictions or descriptors of a phenomenon or how it works. And so we, when we thought and we read a little bit more and we actually observed scientists working and science education contexts in which modeling was going particularly well, we started to notice that really in those contexts, what happens is we bring a person, a cognitive agent, a thinking individual, into this system. And that models actually are constructions of the human mind, usually collaboratively, that are used by cognitive agents in order to explain or make sense of a phenomenon. And so we've come to call this as a shorthand in our conversations about modeling the of-for distinction. And so let me say a little bit more about that. We, of course, want to be positioning students as that cognitive agent, the one who understands what the model is being used for in a classroom and how it can help us account for, understand, and interrogate a phenomenon. So we actually use this of-for distinction as a handy sort of rule of thumb or heuristic that we can apply to our own conversations and discussions about how models are positioned in science classrooms. So we call that the models of versus models for distinction. So let me give you an example of that. When we think about the DNA molecule, if we're in kind of a models of framing of that, that scientific idea, we care that students might know the details of the structure of DNA, that it's helical, that A pairs with T and C is paired with G, and some of those kind of details about what Watson and Crick figured out. But Watson and Crick weren't trying to figure out the structure of this molecule for its own sake. They were using and developing, along with Rosalind Franklin, a model of the DNA molecule that was for understanding how a molecule could serve as a hereditary material. And so if we position models in that way, our model may or may not have some of those details in it, depending on what aspect of heredity or inheritance we're trying to figure out. So if we're trying to figure out how traits are passed from one generation to the next and how a molecule can encode information, we're going to have different considerations for our model than if we just care that students know the details of what the model looks like, or the DNA molecule looks like. So that's an example of our sort of for distinction. So to map back to the thing that we were talking about earlier, really when we think about talking about models of the solar system, or a model of the atom, or a model of food chains, or something like that, we are really positioning students in that knowing about or information frame, and we're in a transmissionist mode. So we might have a model in our classroom, but we're teaching kids about that model, versus when we can say what the model is for, and that for phrase has to be linking it to a phenomenon in the world that we're wondering about, then all of a sudden we've transitioned into more of a sense-making frame. And we've got we can position students as the agents of their learning in that way. So I want you now, using the chat window, to think about the models for just these two that were on my earlier slides. So we might call, and I'm not trying to say that calling something a model of something else is incorrect. It's a perfectly legal way to speak in the English language. But I am challenging us to think about what, if my goal is that kids have a model of the solar system like the one depicted here, or of the water cycle, what is it actually intellectually for the students? So maybe try this out and sort of see if you could think about what are some phenomena in the world that if you had a model of the solar system like this, you would be able to account for, or if you understood the stages or the parts of the water cycle, what are the phenomena in the world that you could use that model for? So see if you can play around with some ideas in the chat. I'll give you a few minutes. So I'm seeing lots of interesting ideas come up in the chat. One of the things I think that's fun to kind of challenge ourselves around is not to use a science word. So not to say this is a model for understanding Newton's whatever law, because that's not something we can see, right? But you could say, or models for understanding condensation, but we could say understanding something about the water cycle gives us access to, it's a model for how water moves around. I've seen some interesting things that people have put in the chat, a particular ecosystem, or why some parts, why climate is different in different places based on how the water is cycling. So these are, this is sort of a challenge I want to put to you all as you think about bringing modeling into your classroom, is to consider how you can position the model with regard to a phenomenon. And we're going to go a little deeper on that right now. So again, we could apply our models for orientation anytime we see something that is traditionally called a model in science. We can ask ourselves, what is that model for? What phenomena does it help us understand? So when we go to the NRC framework and our big master guide to the NGSS, this is a quote from that document. Models serve the purpose of being a tool for thinking with, making predictions, and making sense of experience. And in another a little bit later, it says scientists use models to represent their current understanding of a system under study. A system under study is another way of saying a phenomenon, to aid the development of questions and explanations and to communicate ideas to others. So again, models serve the cognitive agent in a particular way with regard to the phenomenon, and if we keep that person in the center when we think about that for issue, then that gets us a little ways. So we have developed a framework that we use in curriculum development that uses this model for as it's at its heart and tries to help us instructionally remember to make connections between the phenomenon that we're interested in exploring, the person who's interrogating that phenomenon and wondering about it, so that's our cognitive agent, hopefully that's our students, the questions we might ask about the phenomenon. So this is important and something that we didn't quite, when I first started doing modeling work 20 years ago, we didn't have as strong of an emphasis on this question aspect. But as we've worked over time, we see that the way in which we interrogate or wonder about a phenomenon has everything to do with the kinds of questions we ask about it. So an example I often use is the idea of the sunset. We could be looking at a beautiful sunset, and we could wonder all kinds of different things about that sunset that would invoke different models. For example, we could wonder, why is it red tonight but not last night? Or we could wonder, why is it there in the sky, positioned between that house across the street and the water tower in the distance, when last, 2 weeks ago I noticed it was on the other side of the water tower at sunset? Or why is it happening at 5:42 p.m. tonight? So depending on which question we ask about the phenomenon, that will dictate or mediate the kinds of modeling work we do. So once we have a question, we can then work on our model. And we've depicted this in a triangle for a very specific reason. There's no start or stop. There's no place that you begin and place that you end. You're iterating or moving around this triangle all the time. And when we think about science, we know that that's how scientists work, right? They sort of look at something, they wonder about it, they get some ideas out on the table about it, they test those ideas, they ask some different questions, they look at new phenomena, see if it could apply, and they're constantly moving around these intellectual spaces. So we've used this framework in our curriculum design to keep us grounded to the practice of modeling, but also to the other practices in NGSS. So you can imagine there's robust investigation, explanation, argumentation, data analysis, computational reasoning, and communicating connections that we can make by orienting ourselves around this triangle. So in this framework, the models are tools for making sense of phenomena defined in very specific ways by the questions we ask. Okay, deep breath. Let's pause for some questions. I will.
Yes,
Should I
please,
turn off
Cindy.
my
That way
mic,
we'll
or?
avoid feedback. So we're going to pause for questions from the audience. As they come up, I'll try to read them out for Cindy and then give the microphone back. So I see we're still posting questions in response to that earlier prompt. So now we want more general questions about modeling. We'll give you a moment to think. There's a question about how are the models related to core ideas, and that's from Ted Willard.
Hi, Ted. So the way we think about this when we work to develop lessons for classrooms is that the disciplinary core ideas often are stated as kind of the outcome of modeling work, so that one might have done. So underneath a statement like, I'm not going to be able to come up with something off the top of my head, but if we think about disciplinary core idea around natural selection and the key features of natural selection, embedded within that are sort of the key pieces of the model of natural selection. And our job instructionally is to find ways to motivate that learning about that disciplinary core idea with phenomena and help the students sort of get to those particular ideas through their questions and investigations.
Terrific, Cindy. We have a second question, and it just disappeared. Let's see. Do you recommend a certain framework or one that helps with progressions like we see for the science and engineering practices in the NGSS? So how would you, I guess, progress modeling across grade levels?
Well, I actually think the NGSS Appendix F, or that's what it is, right, has done a nice job of thinking about how modeling looks different from young kids on up. I would say that there is a little bit, both in the framework and NGSS, the potential to interpret the modeling language there in that models of or depiction descriptive place. And that is more or less appropriate depending on how old your students are. In other words, describing the pieces of a system might be the model 4 when you're very young. Describing the relationships between those pieces is something you're going to layer on as you get older. And then invoking sort of invisible or unseen entities and aspects of those relationships and connections. Again, you're going to get more layered on as you get older. So I actually think that the progressions that we see around the practices are actually quite useful.
Okay, there are a couple more questions, but I will copy those and try to bring them back during our next question and answer session.
Okay. And we will continue on. So this is a transition here back to Jen. So just in case she didn't sing her own praises enough, I'll sing her praises a bit. So Jen has been working with us for a long time at UC Davis, developing curriculum and figuring out how to actually implement the practice of modeling in the classroom. And she's just been instrumental in making sure that those of us here at the university are actually attending to the realities of complex classroom instruction, and she's just phenomenal at that. And so when we were planning this web seminar, we were talking about what are the things that need to be in place to support modeling in the classroom. In other words, what kind of classroom culture do I have to have? What kind of supports and tools can I use? And so Jennifer's collected a number of these and is going to talk with you about those now. So I will turn off my mic and turn it over to Jen.
All right, thank you, Cindy. So the first thing that I want to talk about is that this is really, well, for a lot of you, you're already modeling, doing sense making in your classroom, and so you've already figured out, hopefully, that it's really a mindset, that what takes place in a classroom that is doing science modeling, it is not school as usual. If someone walked by your room and was able to peer in through the windows They might wonder what the heck is going on inside that classroom, because it does not look like a bunch of students sitting there bored. It does not look like a bunch of students sitting there raising their hands, ready to regurgitate some knowledge back to you. It looks more like what's going on, what's going on here in this picture, where we have these students sitting at desks facing each other, or over here where we have students working together trying to solve a problem, or at the bottom photo where we have a whole classroom discussion going on, where students are really trying to make sense of the science. So one of the ways to look at this PQM triangle with the actual things that are going on inside the classroom here is you do not have to always start at one specific place on the triangle by any means. But I have found in teaching biology that it's been easiest for me to start with a phenomenon of some sort. And once the students observe that phenomenon, it could be stories, a video, a reading, data. Data is my favorite. From that, then we start to come up with questions about that phenomena. We really start to wonder what's going on. And we come up with a question that we can all agree upon that's going to help us really make sense of the most of what we're wondering about. And then once we have that question, then we start brainstorming. Okay, how can we answer this question? What kind of statements can we make that is going to help us make sense of that phenomenon? And we call these initial model ideas. And after we have our brainstormed initial model ideas, then with guidance, we can start to test those ideas. We don't necessarily, as a teacher, I don't say, oh, that's a bad idea, that doesn't work, nope, that's not right. I would never do that with my students. I want them to explore. I want them to figure out what's going on. So with guidance, the students will begin to test their ideas in a variety of ways. It may be investigating. It may be developing and organizing their own investigation and collecting results. It may be through discourse. It could be through a reading that the students then talk about. And of course, it always involves lots of data. As the students start making sense and making sure, yes, this model idea, fits with the data, we're going to keep it, we start to revise the model. So if we have several ideas that kind of sound the same, we'd revise them into one or two ideas. And if something makes sense, we're going to keep it. If we've learned that something doesn't make sense, we've tested it and we're like, nope, that does not make sense, then we're going to throw it out. So there's a lot of revision that goes on, and it's constant as we test the ideas. And then once we have a really good working model, and the reason why I say working model and not final model is because I've realized the models are never really final. At some point during the year, we may come back to an original model and say, hey, I think we need to add something to this, and so we may add to it. So they're really living working models. But once we have a pretty good working model at the moment, then we can use that model to answer our driving question way back here, and also use it to explain the phenomenon that we were wondering about in the first place. All right, in order to really be successful with modeling in the classroom, we've found that there's three key things. Communication and collaboration are huge. Tracking student thinking over time is very important, and I'll speak to more of that in a little bit. And then also making their thinking visible is also very, very important. All right. Communication and collaboration. So I was very excited when I learned that on May 10th, there will be another NSTA webinar that is titled, How Do I Promote Student Discourse? This is huge, not only for NGSS, but also for Common Core in general. And so we're going to talk a little bit about that, about communication and collaboration. Super important if you're going to be making sense of things in your classroom. the first thing, of course, is to establish emotional safety. If students don't feel comfortable talking with each other and sharing their ideas and being willing to be wrong, then it's going to be really hard to develop some of these ideas with your students. So establishing emotional safety is important. Also, developing group norms is also very, very important, or agreements. And if those come from the students, that's all the better. Then it's also important to practice those communication skills with non-science subject matter is usually helpful, because what that does is that helps establish that emotional safety where those students feel really comfortable talking to each other. And then finally, for whatever collaboration or communication strategies you're going to use, have protocols in place. Have them either on a poster or a whiteboard, or if you have them on a PowerPoint slide. But this will really help the students remember, okay, what am I supposed to do in this discussion? Having those up there will have less wonder and more action with your students. So I'm sure a lot of you have several ways that you have your students talk in the classroom, but I wanted to share just a few. For me, I always find, oh yeah, it's great that somebody uses that too. It's nice to have some affirmation to some of your strategies. So the first one that's important, and I'm going to go back just a moment, and I'm going to say that when I first started modeling, I thought, oh, my students know how to talk to each other, and I really just kind of skimmed over this important work. And when I really got into modeling every single day in my classroom, or almost every day, I found out my students really didn't know how to have good conversations. And so when I started the next year and I went through these strategies and practiced with my students, it dramatically changed not only the atmosphere in my classroom, but my students' learning. So this first one is just the art of conversation, and this is just about how to talk with your partner, how important it is to, when you ask a question and you get that answer, to pause and to paraphrase back to your partner, making sure that you heard them correctly, and also letting them know that you heard them. And then the third one, of course, is to probe. Ask another question. See if you can go a little bit deeper. And when we practice this, we always start with something silly like maybe, what is your superpower? And that gives the students a chance to ask questions that are very non-threatening. And then when we work up to more scientific type questions and discussions, then they feel much more comfortable talking to each other. Think, Pair, Share is a very popular one, and of course that's just when students, you ask them a question, they think, they write it down, or they think about it in their head, they pair up with the partner and share it. And of course what's important about this one is that when the facilitator asks for the pairs to share their idea, it's not just one student, but it's really, you know, my partner and I think this. I've seen this used at all grade levels, and it's very, very powerful. The last one is the talking sticks. And this is the one that I kept going, oh, no, I don't need to use this, I don't need to use this. And then when I finally did implement talking sticks in my classroom, I found that this gave a chance for those quiet students, your introverts, the ones that sit and are really quiet and don't say anything and don't seem to want to participate. I found that they do. It's just that they're quiet and they need time to think, and they need a space in which to speak where they feel comfortable and they know they're going to be heard. And with talking sticks, that happens. Because each person, they place a stick on the table in a circle, and as they take turns, they pick up that stick and they talk. They say, give their ideas. If they don't have any ideas, they could paraphrase what the person before them said. That's completely legitimate as long as they speak. And then they keep their pen in their hand so everybody knows that they talked. And then once everybody is done, and you know, because everyone has a stick in their hand, then you can open it up for more discussion. So this is a really powerful way for students to talk to each other. All right, a couple more points. Tracking students' ideas over time. This is important really because, I'm going to jump down to this one right down here, because students have misconceptions in science big time. And one way to really combat those misconceptions is for them to see how their thinking has changed. What was their idea in the beginning? And how do they think about it as they're working through the model? And when they have a working model, what does that look like? So a couple of ways to do this is to have small groups or whole class ideas documented on chart paper or PowerPoint slides. You can also have individuals record their ideas on doodle sheets or interactive notebooks, and I'll explain that in a moment. And then also when students, again, can see their thinking and how it changed, it really does combat those misconceptions. And it also allows for group and individual accountability. A lot of the sense-making in the class is a lot of group work, and quite often teachers say, well, how do I know my students are participating? Well, when you're tracking their ideas over time on their individual papers, that's easy enough. And when they're doing group work, if each student has a different color marker, then you know they're each participating because you can see that their color is on that piece of paper. So let's take a look at a couple of examples here. First one is tracking their student ideas with PowerPoints. This first one here is initial model ideas, brainstorming that they took down. And these were recorded on a PowerPoint, of course. And then over time, this is not our complete working model, but this is a developing model. Their ideas have changed. And so we can go back and look and say, wow, we said this, this, and this, but now we know that maybe that's not really how it works.
Can I pop in real quick, Jen?
And we can also
something else about this. So
go ahead.
I think I'm seeing questions in the chat like, well, how did you do that? Like, how did you move them from here to there? And this is when they have opportunities to examine phenomena, investigate those phenomena, look at data, analyze data. All of those things are the inputs and the things that are helping them change their ideas from some of the initial ideas they had about the system, maybe from middle school or maybe just intuitive ideas they had, to a more sophisticated or useful set of, or complete set of ideas. So it's actually interacting and doing investigations and maybe a reading or all kinds of different ways you can give them some more inputs. They're doing a simulation. In this case, they were looking at graphs of the finches on the Galapagos. They can begin to refine those ideas over time. And so showing them how their ideas have changed is really powerful for their learning.
Thank you, Cindy. So this is another way to track their ideas on chart paper. And this is really important for them to see really what their initial ideas were at the very beginning. And then this is our but our working model. And this has to do with how do species change over time. And then I spoke about individuals having their thinking tracked over time. And a couple ways to do that, of course, is either if you keep a science notebook, interactive notebook, or we developed some things called doodle sheets. And we find doodle sheets really important because these completely belong to the students. I mean, I will collect them and I will give credit, no credit, but I don't grade them because this is where students write down their ideas, draw pictures, learn from a partner and write their ideas down, cross things out, add new ideas. This is really for them to take a good look at their individual thinking because, again, so much of the work is group work and group thinking as well. And then the last point that I wanted to make about how to really support your students with modeling in the classroom is about making their thinking visible. One of the first things that teachers think about with modeling is so much of this is done in the classroom with groups. Oh my gosh, what about those absent students? Because we all have them. And when we make their thinking visible, when these absent students come back to school and they walk in the room and they can see that there are posters and charts on the wall, it is a way for them to review or to look over what they did before they left, and then also kind of see, oh, that's what happened when I was gone. Oh, those are the ideas that they came with. It's not perfect, but it is very, very helpful. And of course, you can also make their thinking visible on things like Schoology, whatever kind of system you use to share ideas or have chats with your students. So the model-based lessons, again, they're about reasoning. They're about using this information that is around the room in text, in data, and using that information to then come up with an explanation for that phenomenon. So as with Common Core as well, it's about pulling those ideas in. I know that some teachers, when they get to their final for their classroom, they may pull all the models off the wall, knowing that the students have worked with them enough to use them. And other teachers don't. They always leave them up feeling that, nope, I always want my students to be able to look at those models and be able to use them, so they're not worried about memorizing, but what they're really doing is they're really thinking and reasoning with those model ideas. Students can also record their ideas on whiteboards or chart paper, and those can be displayed in the classroom. And what's really important is that once you have your working model, that you keep those relevant materials plus those working models posted in the room. Find a permanent location. And this, oh my gosh, this can be challenging. Sometimes you have to layer them, but at least they're still there. And if a student really needs information, they can walk up to that poster and go down a couple layers and find the information they need. So I have a couple of pictures of what that looks like. Gallery walks are a great way to allow your students to see, for you to see what they're thinking, and more importantly, allow other students to see what other students are thinking. This is a slide of a student that is using several resources around the room to explain how two alleles can be codominant. So he's using lots of resources and making his thinking visible to the students, and it not only helped me to see if he made sense of what was going on, but even better, other students could make comment, ask him questions, and he could revise if he needed to right there on the spot. And then finally, this is a working model for photosynthesis, and this would be posted in my room, and it would be left up for the rest of the year, except, of course, when we had mandated state testing, all that was taken down, of course.
But actually, I want to say something about that. That you told me a story about this a long time ago, Jen, where I think it was the first year you'd done modeling in your classroom and you'd developed a model of natural selection, and it had been up on your wall all year and you referred to it here and there. And then when the state test came around, you had to take it down. But you could tell when the students had gotten to those natural selection questions on the exam, because they would sort of peer and ponder at the spot on the wall in the room where that model had been. So it was like a power, and not because they were like hoping it was there listed for them, but because it was like a trigger, a way for them to kind of conjure and think through the really cool work they had done to develop that model to begin with. And that story's always stuck with me as a way to think about how powerful it can be for students to feel like they're building knowledge over time and to keep that visible in the classroom.
Yep, thank you for that reminder. That was a pretty special moment for me, for sure. All right. Do we have some questions?
Yes, Jennifer, I've been trying to keep track of them as we've been working, and I'm sure more will get posted. There were quite a few questions that came through to ask if a sample of the doodle sheet might be made available. So quite a few people asked for that, if you'd be willing to share any of those.
Of course.
Well, and I'll say something too, this is sort of a shameless plug, but at the end we'll have some websites for you to go to, and one of the projects that Jen and I have been working on together is, we've been talking a lot about biology, so you won't be surprised to hear it's a biology curriculum project, and there's a sort of modeling toolkit that we have on that website that has a description of how our teachers use that doodle sheet tool in that curriculum.
And if I could add something real quick as well, the work that was done with the doodle sheets and everything else, just like we ask our students to collaborate, it's so important for teachers to collaborate, to come up with these lessons and ideas. It just makes the curriculum so much stronger.
Thank you. There was a question earlier on about whether or not you could give some examples of the phenomena question model triangle, possibly in physical science, if it's harder for students to visualize.
It's so funny because over the years, The reason we moved into the realm of biology is because people kept saying to us early on in our modeling work, oh, it's so easy and straightforward to do modeling in the physical sciences, but man, biology, that's a tough one. So we're like, okay, well, let's take on that tough one and try that. And now we use biology examples and people are like, oh, wait, what about the physical sciences? So it's all about the space your head is in. Sure, I can give an example of a PQM with physical science. So we've done some work with light boxes and how you see, with very young kids, on how you can see. So the phenomenon is just you have a box, like a cereal box, that you can peer into with a little flap on the top that you can open, and you have a little figure at the end of the cereal box, and when you open the flap, you can see the figure, and you close the flap, you can't, or you could put a light on in the side, or all kinds of different things that they can do with that box. So there's a phenomenon. And the questions they can ask, if they're very young kids, I did this with kindergartners, are very simple questions like, how come I can see it when the flap is open, but I can't see it when the flap is closed? And our very early model for that is we need light to see. And we can test that idea and apply it to different phenomena and see, is it the light coming off of the object to our eye, or is our eye doing something to the object? And how can we test those different scenarios? So we can use shadows and things like that. And so even this super simple system and, you know, what we might consider a very elementary model idea that we need light in order to see, and that's in our DCIs for NGSS, you can spin around that model triangle for something even as simple as that.
Okay, there's lots of wonderful questions. Let's give one more. There was a question about whether or not you've had students develop rubrics or requirements for their models as they revise them.
Do you want to take that, Jen? Yeah.
Sure. I have not had them create rubrics per se. However, for, let's say, the natural selection model that the students, or the change over time model as we called it, when the students answered their driving question for how did the Galapagos finch's beak size change over time, I used a rubric, but in that rubric I just took their model ideas, and those model ideas became the rubric. Idea number one, did they just state the model statement? Did they actually apply it to the finches? So in that case, I wouldn't say that the students developed their own rubric, but I took their ideas and put that into a rubric that then I gave back to them so that they could use that as they were writing their explanation.
Yes, and I see one of our participants answered, Jeanette, that her students set the requirements for strong and weak models based on the Appendix F progressions, which is a great idea.
That is a great idea. The other thing I will say, so one of the things what Jen's talking about, right, is that if you're using a model to develop an explanation, then you're weaving together sort of the model and the phenomenon. And so what she was saying is, like, then your model becomes the way in which you track or check off and make sure that you've attended to all the different ideas and ways that you've been thinking about the system in your final explanation for whatever it is. So for example, in natural selection, you might apply it to a different microevolutionary phenomenon. They worked on finch beaks, but you could do antibiotic resistance or something like that and see if they could use all the same model parts to explain in the new system. So that's one thing. And I think another thing, another way in which sort of, it's not exactly rubrics, but these criteria for what a model needs to do. Jen, you can maybe talk about how you set that at the very beginning of the year, but some of the things we do at the very beginning of the year are set some general things that all models need to do. Again, based on experience we do with, have a modeling experience and then step back from that and say, okay, our model needs to explain the data. It needs to be consistent with what other ideas we have. It needs to be useful as a predictive tool, if that's appropriate in the discipline we're in. And it should be as simple as possible. And those criteria, Jen has some activities and others have used different activities in their classrooms over time, to get those criteria out on the table very beginning of the year, and then we constantly return to them. So every time we're doing a model, have we explained all the data? Does this model account for all the data or just some of the data? And what would we need to do to add to it or continue to refine our model? So those kinds of broad criteria can be specified in the particular context, but are useful as a tool to sort of track our modeling work over the course of the year.
Thank you. Those are excellent answers. I am trying to keep track of questions as they come through. We should keep moving forward, and I'll bring up those questions at the end. And those of you who are waiting for an answer, be sure you post your question again if we don't get to it.
Okay. So one of the things that I've been thinking a lot about recently is what are the incremental steps I can take as a teacher to begin to move toward a classroom that is developing and using models in the way the NGSS is asking us to do that. And the first thing I want to say before getting into a little bit more detail about this is that it's a journey. It's not something that's not a switch that you flip. It's not like one day I'm a info frame, knowing about teacher, and the next day I'm a sense-making modeling teacher. It takes time, and I saw some comments in the chat about how sometimes I feel like I'm in one space and sometimes I feel like I'm in the other. And first of all, I think that's never not going to be the case. You're always going to be flipping around between having expertise in the area and having information to share with your students that's useful, and co-collaborating and co-constructing with them, and that's okay. So Jen can pipe in here too, but when I think about sort of the most important things that, as I've watched teachers change over the last 20 years that I've been working on modeling and model-based reasoning, I've been trying to think hard about what are the important increments, like what are the quick nudges toward modeling, and then how do we know it when we've gotten there. And so I'm just going to go back again to this framework that we've distilled over time to sort of say this can be your nudge, this can be your way to get started. And it's not to say that every single lesson has to be able to be mapped onto this framework, but if you ask yourself, what is the main thing I'm doing today? What am I doing? And we think about this, we call these model moves. Am I investigating a phenomenon? Am I just exploring it at first blush? Am I trying to distill a question from a phenomenon? So there's movement around this triangle that you could think about with regard to your lessons. Do I have a robust question and now I need to go back to the phenomenon to get some more data or do another investigation to drill down on that question a little bit? Do I already have a model to use and can I apply it to the original phenomenon or another one? Or do I need to develop pieces of it? So all of this movement that we can be doing around us, we call them model moves. And so I think some of the productive ways to get started are on this triangle for us. I just want to say a few things about each of the vertices here.
Could I jump in for a minute, Cindy?
Sure, yeah.
And one thing is sometimes you just have to get started. And one way to get started is, I've heard it referred to as ABC, activity before content. Try that. Have the students work with the phenomenon. Don't give them background. Just have them do a typical lab that you have them do, and you might see the phenomenon there, which would be pretty exciting. And the other part is you may be in the middle of the lesson and go, oh my gosh, this is the phenomenon. And if you can take a moment to change your lesson around to try working it through a PQM model, go for it, or make notes and know that next time around you're really going to base it around the phenomenon. Thanks, Cindy.
Yeah, so we often find, and I think that we're seeing this at NSTA a couple weeks ago, there was a lot of talk about phenomena and the importance of them. I would say exactly what Jen just said, that being clear about what the science ideas you want kids to know actually explain in the real world it's super helpful and probably the most important first step in terms of modeling. Sometimes I think teachers are like, well, I don't know what the models are. Like the DCIs are written a certain way, or my textbook scope and, or my district scope and sequence, has topics listed. Like, I don't know how to make those things models. And I would say you can't know how to make those things models until you're clear about what it is in the world that you're trying to explain. And so you have to start with a phenomenon, but you can't end with a phenomenon. In other words, you have to wade into the messy space of the real world, but pretty quickly you have to bound it and pull it in and be clear about specific aspects of that thing that you're trying to account for or understand. So a lot of times people also say, like, I don't know what the phenomenon is for, well, we had a question at our NSTA talk, for Le Chatelier's principle, whatever. So I would say, well, what was Le Chatelier looking at? And that's what I mean by the history of science being super helpful. The scientists, and we know lots of canonical stories about scientists who came up with particular ideas that we want students to know. Go back and read those stories and wonder, what was the scientist examining? What were the data they were using? What was the thing in the world they were wondering about when they came up with this idea? We have, stories about Newton and apples falling on his head, which may or may not be true. Mendel and his peas and things like that. Some of them we can just rattle off and be like, oh yeah, the scientist Darwin was looking at the finches on the Galapagos Islands. But sometimes that access to that phenomenon isn't part of the story that we often tell about that scientist. But there are history of science texts and stories from the history of science that can be super helpful. Or even just the thought experiment, like, what was that person? What does it help me explain in the world? And make that move from the sort of science content that you want kids to know toward a phenomenon. And then, again, I want to emphasize the role of the question in helping us zero in and be specific about the particular aspects of the phenomenon we're interested in or trying to understand. For the models themselves, when people are trying to figure out, like, I don't even know what models I should do or where I should start, if you're an NGSS adopted state, I actually, sorry Ted, I'm going to maybe speak blasphemy here, but I don't think the performance expectations are the place to start. I think you should go to the framework and the descriptions of the disciplinary core ideas. And it's a much more generative and holistic space around the science ideas that will help you think, I want kids to develop a model about the particulate nature of matter, or about, I want the kids to develop a gas laws model, or the behavior of fluids, or something like that. I'm out of my element here, so I might be spouting nonsense. But I want, I think, and we have used very productively the words and the descriptions in the framework of the disciplinary core ideas as a way to begin. Sometimes the chunking and the specificity of the performance expectations in NGSS feels limiting. And so other people talk about this in terms of bundling NGSS performance expectations. So that's another kind of another way to think through the idea that the piece that's in a performance expectation might not be a model-sized piece. And then I would just come back again to this idea that we want to push on and continue to foster the notion that models are for explaining things in the world. They are not endpoints in themselves, and that the modeling process, if you're doing it right, is going to end, if there's an end, with an explanation for the phenomenon or an answer to the questions you've been asking about the phenomena. And that if you can't make it all the way around this triangle, then you've done some aspects of the modeling practice, but not all of them. So when we think about getting started on this journey, we actually think the heuristic, the models of versus models for, is a really useful tool you can use to ask yourself what you're doing in the classroom. So if you have a physical object in your classroom that you're calling the model, what is that thing doing intellectually for the group? And then using this triangle as an entree into actual planning, where you're trying to push on being clear about the connections between the model, question, and phenomenon. So that's kind of what I have to say about getting started. So I want to push it also, I didn't really prime you for this, Jen, but if you have any other comments, Jen, about how to get folks, or how you got started in the practice of modeling.
Oh, big question. Well, it was really from taking your classes, Cindy, and then being involved with the collaborative group, and I guess seeing the examples that when I saw, I was really frustrated because my students weren't thinking. They were just sitting there, and the A kids could regurgitate and spell things back to me, but I didn't think they'd really learned anything. And so then when I started playing with the idea of giving them phenomenon, giving them something to really wonder about and ask their own questions, that's when the students really became interested, and I didn't let them off the hook. They had to discuss it. But it's a challenging journey, but it's definitely one worth doing. And once I started working with one model, the natural selection, I had to find other ways to do modeling in my class to have my students make sense of phenomenon. And then I couldn't stop there. I teach a forensic science class, and I started converting all those lessons into more of this PQM framework as well.
Okay, I think that we are ready to have some more conversation. We just wanted to acknowledge that Jen and I work on an incredible team together, one of whom just passed away, Wendell Potter, who is a physics professor here at UC Davis and has done some incredible work in undergraduate modeling in the physics world. And we lost a great thinker there. But we also are very appreciative of our NSF funding, and we've got some places that folks can go to look at some of the work that we're doing. The model-based biology, the high school biology curriculum will be totally available at the end of June, but you can go to the website and see some pieces right now and what it's going to look like. So I think that's where we are. Maybe we can have a few more questions.
Thank you so much, Cindy and Jennifer. Cindy, if you could turn the microphone off. I just want to outline here that we've got a few more web seminars coming up. We've had Cindy and Jen discuss today about student modeling, but this continues on May 10th on how to promote student discourse with Kate McNeil and Eric Meese. And on July 12th with Brian Reiser and Michael Novak, we'll discuss how do I develop a storyline for a unit. I think Cindy will recognize all of those people's names in all of this, and this will all be sort of a set of how do I. I'm going to pass things off to Dorothy here, who will explain how to do the survey, and then we'll have our presenters back for a few questions after that.
Hello, everyone. I'd like to thank today's presenters, Cynthia Passmore from University of California, Davis, and Jennifer Horton from the Western Placer Unified School District. We are going to take a few moments now to do the evaluation survey, and then we'll come back for question and answer. We also want to thank our sponsor of today's web seminar, Carnegie Corporation of New York. And thank you also to the administration of NSTA for the support of web seminars. I'm going to be stopping our recording now, and we'll go to our survey.